We're going to start out with some general stuff about dimensional analysis. Every question we have been working through is designed to fit this format. Every single one. Okay? So when you read a question, what you're looking for is, what is that desired measurement and substance? Then you're looking at what the given measurement and substance is. So what do I want? What do I have? Okay? That establishes our beginning. So those are our starting questions. What do I want? And then we start with, what do I have? The what do I want is placed immediately. Whatever it is placed in the numerator or denominator depending on what you're being asked for. Typically is it being placed in the numerator, so over 1. The what do I have? Okay. Typically at this stage we're really only given, quote unquote, one thing. Okay. So in the absence of matching either the measurement substance, the measurement unit, or the substance unit, we'll start with placing that in the numerator as well. Okay? So those are the first two questions that we ask ourselves. Okay? The next question would be, are they the same? Or perhaps a little bit different, or sorry, not that word. How are they different? Okay. Once we know how they are different, we now have a place to go, because that how are they different now sets us up for a conversion factor. Okay. And depending on the difference, be it the substance or the measurement, we're going to have a different pathway to go through. Because the substance is a much narrower range where you can convert, there's only one place you can convert a substance, okay? I would recommend that your first step would be to deal with your substance conversion, okay? If you need to. If you don't have to convert the substance, then don't worry about it. Worry about the measurement, okay? The question then becomes, if it's the substance, well, what do I want? Over what do I have? By answering those questions, I can now place units into that conversion factor. The placement of those units will now allow me to say, is this a conversion factor that exists? Okay? If I can't answer that question, then yes, you are dead in the water. There is nothing you can do. Okay? At that point, you're guessing, you're throwing stuff at the wall and hoping it works. Okay? This is why it is important to know where to find those conversion factors, which is why every time we solve a question, what do I write underneath each conversion factor? Where it is found. We see BCE, balanced chemical equation. Okay? We see given, because it was given information. Okay? We see PT, because it was the periodic table. We see memorized, because we were required to memorize that information. We see front of the exam, because it's on the front of the exam. Those are things that you have to know and you have to bring in. But these are the questions you're asking to get that information. All too often, and what I'm seeing with people's work, is that you're immediately trying to drop the conversion factor in. That assumes you've already answered those questions. And in most of the cases that I'm watching, when you start dropping in those numbers, your assumption was horribly wrong, which is why your entire process crumbles, because you aren't asking the questions first. You have to ask those questions. Okay? Everything we've been doing is asking those questions. Okay? What happens after we do that? Well, now units cancel. Okay? Potentially. What if the units don't cancel? What would the question then be? Well, what do I want? What do I have? And we run another conversion. Then we attempt to cancel units. Okay? Do we have the answer? How is the left and right different? If they're different, I need a conversion factor. What's that conversion factor? What do I want? What do I have? The entire process is asking you those exact same questions all the way through. Okay? And so now I'm going to ask an awkward, unpleasant question. Nobody wrote any of that down. How many of you can solve that question in under 5 minutes? That's a problem. Okay? The biggest problem there is that you aren't writing down those questions. You aren't establishing what that process is because you aren't taking any notes on what the process is. You're only taking notes on what the answer is. That is a phenomenally great thing. You now know how to copy answers down. The test doesn't ask you for that. The test is asking you for that process. Okay? Before we get too excited about solving this question, we've already done it. Okay? It was only used as an example to draw attention to the fact that you aren't taking notes where you should be taking notes. The notes are what are those questions? How do you establish that process moving forwards? That's what you need to take notes on. Okay? So, what are we doing? We're looking at that conversion process on how to solve a question. The ideal format is dimensional analysis. And the reason being is that dimensional analysis setup, that whole conversion process, works for 95% of the questions you will ever encounter. Okay? And I don't mean ever encounter in chemistry. I mean ever encounter. Period. Full stop. All of them. One of the biggest problems we're seeing in later chemistry courses is people being like, well, I don't know how to convert this because I don't know the formula. Because there isn't a formula. That over-reliance on a formula is saying that you want to memorize a fact. Okay? I hear people complain about education all the time. Education isn't teaching students how to do things right. No, students are trying to find shortcuts through the system. I fully understand because I was there and I did it. Okay? But what we're trying to set up is a path that removes some of those shortcuts. Okay? And the reason why we need to remove those shortcuts is not because we're trying to make life difficult, but when you leave the class, you won't have the shortcut anymore. That shortcut holds no value outside of that classroom. Okay? That's where education is failing, is because you're looking for shortcuts. Stop looking for shortcuts through the education process. Okay? You get out of the course what you put in. What you need to be putting in is finding that process. Okay? And that sucks. Okay? That is painful. But that is what we're trying to work through and get. Okay? So, how do we convert the A to B? This comes from that equality. This is why we talked about those equalities, which gets us two conversion factors. Well, which one do we use? The one that we need to allow us to solve the question. What do I have? What am I given? Or what do I want? Okay? So what are some conversions? Inches to feet. What is that conversion? 12 inches equals 1 foot. Where did you have that conversion factor? You've memorized it. How long did it take you to memorize that? In elementary school. So, oh, it was elementary school, it was easy. Was it in 16 weeks? No, it was probably in your elementary school process across 5 years. Okay? So that thing that you've memorized is great. Okay? It's a conversion. What we want you to be able to do is to find those conversions. Not to memorize them, but to find new ones. Okay? That's what we're trying to teach you. Elementary school set it up with the basics of it so you could understand those patterns that hopefully you would then be able to build on. Okay? What's another conversion factor? Milligrams to grams. Where's that one come from? Okay, so we could go with 1,000 milligrams is 1 gram.
But that's a pure guess, and I could be wrong.
What's that?
That's a guess, and I could be wrong because.
Okay, so we could be wrong. So this is one of those things where we have to have a process behind so that we can memorize it as best as possible. This is why when we talk about it in class, I actually said you should memorize what the Greek prefix mean. And what does milli mean? 10 to the negative 3. Where's our power of 10 go? With the core unit. 10 to the negative 3 grams is 1 milligram. Those two conversion factors are identical. And the only reason they exchange in their different locations is because, or that power of 10, because 1,000 is ultimately 10 to the third, is because of how our human brain functions. Okay? Most of the calculations that we run, we don't have to do in our human brain. What do we have to use?
Calculator.
A calculator. Okay? So you can take advantage of that tool to help you manipulate things. When you lose that tool, then fine. You need to come up with other systems to manipulate. Okay? If we lose that tool, the ability to have a calculator with us at all times, I think we're going to have some larger issues than how to convert milligram to gram. Right? What might our larger issue be? Why would you not have a working phone? The battery died. Okay? But can't you charge the battery?
Or if it's cut off.
So what if your electricity is cut off? Would you need to be able to do that? Yeah, we could do that conversion. But are you going to have a larger issue if you don't have electricity? Yeah. How do I cook my food? Where the hell is my food? Right? Almost all of my food is cooled and conditioned by electricity. Okay? So we have those tools, use them. When we lose those tools, we're going to have a lot larger issues. And the issue here isn't going to be how to convert milligram to gram. It's going to be how do I butcher a cow? Okay? So if we want to talk about useful skills, none of you are learning that useful skill. Because we're making the assumption that we're not going to need to learn how to butcher a cow. Okay? So we're trying to build on that information, use the information that we have access to, or the tools we have access to build further and memorize less. Okay? Which could easily come back and bite us. Okay? But we have to make some assumptions to simplify all the crap that we have to deal with. Okay? What other conversions are there? Because if we look at all three of these conversions, what do these three things convert? Those are all measurements. Right? Measurement conversions you've done your entire life. This is a chemistry class. I don't care about measurement conversions. It's a bit overstated. What do I care about? Substance conversions. Can I convert hydrogen into water? Or potentially more importantly, yes, I know it's inequality, it doesn't really matter. Could I convert water into hydrogen gas? Why might I want to do that? You heard of a hydrogen fuel car? Yeah? Why would we want a hydrogen fuel car? What's the point of those? What's that?
To stop using gas.
To stop using gasoline. Why are we stop using gasoline?
It's a finite resource.
Finite resource. Bad for the environment because it produces CO2. So why might I convert water into H2? Well, hydrogen can now be used as a fuel in cars, and in its process, it just goes back to water. So it's phenomenally green and clean. That's fantastic. How do I do that conversion? Where would I find the conversion between water into H2? What's that? Okay. One option is I could look at the chemical formula. Okay, if I look at that chemical formula, doesn't it say H2 right there? Is the H2 in water the same as H2 shown there?
No, because it's compounded with oxygen.
Okay, which means the H2 in water, is that actually hydrogen gas?
No,
No, what is it?
it's two hydrogen atoms.
It's two hydrogen atoms bonded to an oxygen. What is H2?
Hydrogen gas.
Hydrogen gas. Those are entirely different substances. So this now brings in more meaning. When we look at this H2, this is not the H2 there. If I had said hydrogen atoms, then yes, the chemical formula would have been fantastic. The chemical formula is a great source for finding conversion factors. That conversion factor would require that that said H. Okay? Now the chemical formula would work. There's two H and one H2O. Have I included a measurement unit yet? Nope. Every unit requires both a measurement and a substance. What is the measurement unit? H would be the substance. What is this H? It's an atom. So we could say two atoms, of course there's not enough space to write that, atoms of hydrogen equals what? One, we could call it a compound of H2O. Okay? We talked about that as a unit. Does it make sense to look at atoms or compounds in chemistry?
Yeah.
Yeah? Because when I walk into the lab, I can measure an atom. Okay? I think we talked about it. How expensive is the balance to measure an atom? $19 million. Okay? It's pretty close. Order of magnitude. I'm usually okay with that. So that's not particularly easy to do. So are we going to be able to measure atoms and compounds? No. So what unit do we use as our substance or as far as our measurement? Somebody mumbled it, yeah? Moles. 2 moles of hydrogen atoms is 1 mole of water molecules. We're now talking about chemistry. That's chemistry. The dimensional analysis stuff is the process on how we use chemistry to solve questions. Okay? That equals thing, that's chemistry. That's all we're talking about. Okay? Can I find just hydrogen atoms floating around in the earth? No, because what are hydrogen atoms? When I find hydrogen in its elemental state, what is it with? Another hydrogen, because hydrogen is diatomic, which means, would I ever be able to use this conversion? Do I get hydrogen atoms?
No.
Nope, which means while this is a valid conversion, is it one that actually is useful?
No.
No. I would need, to make it useful, I need H2. Okay? But H2 isn't found in H2O. Because H2 is hydrogen gas. H2O is 2 hydrogen atoms bonded to oxygen. Where do I find the conversion factor that relates? So where do I find the numbers that could potentially relate those 2 different substances? Looking at the periodic table isn't a bad idea necessarily because there's lots of useful stuff there, but the periodic table relates mass and our substance. Here, it's all one substance. Say that?
Balanced.
Where do I find the information to relate 2 different substances from a balanced chemical equation? That balanced chemical equation says I need 2 H2s to make 2 H2Os. Now I have a conversion factor. That conversion factor is my chemistry. I have to be able to interpret that chemical equation to draw that information out. Once I have that information, I use the process. What was the process? What do I have? What do I want? What's the next step of that process? What do I have? What do I want? What's the next step of that process?
What's the difference between?
What do I have? What do I want? What's the next step of the process?
Convert.
What do I have? What do I want? What's the next step of the process?
You have to
What do I have? What do I want? What's the next step of the process?
You get the answer to it.
What do I have? What do I want?
What did you say?
It is literally, what do I have? What do I want? That is the next step. Every time. What do I have? What do I want? What do I have? What do I want? Every single time. It doesn't change. What do I have? What do I want? If what I have and what I want are the same, then I'm done. Right? But I have to ask those two questions. If I'm not asking those questions, I can't solve. Because I don't know what I have and what I want. I'm just throwing stuff into it and hoping it works. Okay? We can't just throw numbers at a question. You have to know what you have and what you want all the way through. Okay? The chemical equation here gives me a conversion factor that potentially allows me to relate what do I want to what do I have. Okay? That's what chemistry is doing. It's addressing that balance between those. Sometimes that conversion factor exists. Sometimes it doesn't. That's why you need to be able to go out and find where those things are. You have to know that information. Just like feet to inches. It took you 5 years to really process and get a hold of that. I'm expecting you to do multiple conversions like this now in 4 weeks. You've been like, wow, that seems really fast. Yeah, that's the end of the semester. Okay, and argue I'm asking you to do that in 2 weeks. A week. Really a week. Damn, that's even faster. What's in a week? Your next exam. Okay? So you have to be thinking along those lines, not just what do I shovel into this equation. What do I have? What do I want? And just establish that process all the way through. If you don't know that conversion factor, that's a separate issue. Now you have to ask somebody who can help direct you. Okay? And the question you should be asked is not how do I solve this question, but saying I have this information, I have this information, I don't know how to convert those. Okay? Or I don't know where to find that conversion factor. Okay? What a tutor should be able to do is go, well, you can't convert those two. Okay? Which means you need a different conversion system. Now I have to deal with a slight switch to the what do I have, what do I want. I'm going to have to find a different what do I have, or find a different what do I want, to establish those relationships all the way through. But it's still the same question. Or a tutor will look at it and be like, dude, you just find out on the periodic table. And you'll feel like an idiot and be like, well, damn it, I should have known that. No, you shouldn't. That's why you're in the class. Okay? By next Thursday, you should be like, damn it, I should have known that. Yes. Then absolutely. Okay? So, our conversion factors. Our units have two pieces, a measurement and a substance. Right? You have to be able to know where those conversion relationships come from. Okay? And ideally targeting which part of the conversion or which part of the unit you're trying to convert, either the measurement or the substance. Okay? The organization, what do I have, what do I want, is dimensional analysis. This thing along the bottom, I attempted to build something like that, and the more I look at it, the more I just don't like it. Okay? But ultimately what this is doing is allowing you to see where different conversion factors could come from. Moles of A to moles of B, what changed? A to B.
the substance.
The substance. Where do I find a substance conversion? Balanced reaction. Okay? Grams of A to moles of A. What changed?
The measurement.
The measurement. Where do I find the measurement conversion between grams and moles? Periodic table. AMUs to grams. AMUs of A to grams of A. What changed? Measurement. Where do I find that conversion? Well, I would need the conversion between AMUs and grams. Do you have that number memorized? No. Okay. So how would you know that? It would have to be on the front of the exam. What if it wasn't on the front of the exam? You got to find a different path. Okay? You have to find a different what do I have, what do I want to try and establish your conversion system all the way through. Okay? That is ultimately what we're trying to do, is find those relationships. I don't like the idea of dropping it in a line because that makes it look like, oh, you just have to do all of these conversions. You don't. Depending on the question, you could be dropped in any one of those individual places. Okay, so a slightly better format would be something like this. To convert measurements, there's tables of them in your book. Metric must be memorized. Which metric? Kilo, centi, and milli. You have to have those memorized. The English conversions, measurements, will be provided on the exam if you're expected to use them. Okay? Numbers of atoms. Where could you find a conversion for the numbers of atoms? That's from a chemical formula. Okay? Because that's what our formula tells us. Okay? Numbers of molecules. Okay? That tends to move to a chemical equation. Okay? Numbers of moles. That can come from formulas or equations. Okay? It could also come from Avogadro's number if we wanted to drop that in. Atomic mass, molar mass, grams to atoms, grams to moles. And I keep botching that one. It's not grams to atoms, it's AMUs to atoms. You're like, I haven't worked with AMUs. That's because it's not a pleasant unit to work with. Okay, so we tend to not use AMUs. We tend to use grams per mole. Okay, that's found on the periodic table. So you have to be able to pull out where those conversion factors are found and use them. Just memorizing that they exist also doesn't help you because you have to then be able to use them. Okay? So, let's stop talking about conversion factors because, hell, they're a pain in the butt. So let's look at water and solubility. If we take a look at water, and in fact we're going to expand out here, water has interesting properties because we have a hydrogen atom and an oxygen atom. Okay? Those two atoms have vastly different electronegativities. And electronegativity was the ability for one atom to remove or take bonding electrons from another atom. More chemistry. So what we're saying is that line, which was our bond, those electrons spend most of their time on the oxygen. Why on the oxygen? It's more electronegative. So if oxygen is now stealing those electrons, what charge does it become? It's effectively gaining electrons. It is negative. Where did it get those electrons from? The hydrogen, which means the hydrogen has now lost electrons. It's becoming positive. That notation looks an awful lot like the notation that we could use for the representation shown over here, where we have a sodium ion and a chloride ion, the plus and the minus. We use that notation for the sodium and the chloride because what is the bond connecting them? Yeah.
How do we identify bonds?
How do we identify bonds?
Oh, depending if it's a
Metal and a metal, ultimately we haven't talked about, so it's not a bad place to start. Metal and a metal, don't know. What else? Metal and a non-metal, or non-metal and non-metal. What do we have? We have a metal and a non-metal. What kind of bond connects a metal and a non-metal? An ionic bond. That's why we can show the plus and the minus, because the difference in electronegativity is so large that they become a full transfer of electrons. If we show the plus and the minus for water, what would that suggest we're saying the bond in there is? Does our representation currently for water look the same as it does for the ionic compound? Yeah. So what would we be saying the bond is in water? We would then be calling it ionic. How did we know we had an ionic bond? It was a metal and a non-metal. Is hydrogen a metal? No. Is oxygen a metal? Can I call that an ionic bond? Nope, so that's wrong. If I can't call that an ionic bond, I can't say the hydrogen is formally positive and the oxygen is formally positive. So I could then remove that information. But by removing that information, I've removed useful things. Is there a way I can alter the notation such that I can still maintain that the oxygen does have some negative charge and the hydrogen does still have some positive charge, but they aren't formally positive and negative? Yes, I can. That notation is known as the delta notation. Okay? It's a lowercase Greek delta. All that's saying is partial. Okay? So when we saw a capital delta, what did that mean? A change in temperature. Ultimately, a change in temperature to mean it went up because we added heat. Okay? We've changed the temperature. When we're looking at the partial deltas, we're now saying these are also a change, but a change in what? Change in charge. That charge can give me useful information. What useful information does that give me? If I take the salt and now dissolve it in water, what happens around the salt ion? What's going to be attracted to the positive of that sodium? The oxygen. Why would the oxygen be attracted to that sodium? The oxygen is partially negative, the sodium is formally positive. Opposite charges attract. These are very much the same as magnets. Kind of like the discussion we had with protons and electrons back in Unit 1 with basic subatomic structure. Yes, it's identical to it. It's the exact same process. Okay? We're looking at those charges attempting to cancel each other out. In the case of water dissolving compounds, the interaction with multiple water molecules is stronger when the salt is dissolved than when the salt is still a solid. That is why it dissolves. Okay? It is a difference in strength of those interactions. Okay? That's why we're seeing solubility. Okay, well, what would happen to the chloride? Should the chloride also be connected to the oxygen? What charge is the chloride? Negative. What charge or partial charge is the oxygen? A negative. So we're going to take the north end of a magnet and say it interacts strongly with the north end of a magnet. Like they're attracted to each other. They're repelled. Is that a good interaction to show? No. So what does that chloride interact with? It could interact with the sodium. If it interacts with the sodium, does the salt dissolve? Nope. Because now all of the chloride is stuck to the sodium. If chloride's stuck to the sodium, what can't interact with the sodium? The oxygen from water. So what does the chloride interact with then? The hydrogen on water. Okay? It is because we have those multiple interactions within our water molecule that allows us to cancel those charges out. Okay? Or to neutralize those charges. That's the point. That's what we're showing within those interactions. Kind of make sense? Right? If we're looking at something dissolving, okay, we're effectively taking a solid and we're turning it into what phase? Okay, you're officially turning it into an aqueous. Where I would argue you're going is you're mirroring roughly what a liquid would look like. It's not formally a liquid because a liquid by definition is, we go all the way back to Unit 1 terms, pure. Okay, a liquid must be pure. Okay, since we're looking at a solution of both water and salt, we can't call it pure. Okay, we could call it a homogeneous mixture, but that's why we have to bring in aqueous. So if we're looking at the dissolving process, a solid is roughly turning into a liquid. What might help the solid turn into a liquid? Man, I've never turned a solid into a liquid before. Like when I drop my ice cube into my drink. what happens? What's that? It's not solubility because it's both the same. Well, we run into some weird things there. We're adjusting the temperature. When you drop the ice into your beverage, what's happening? The ice goes from a solid to a liquid. Okay? That change in phase allows my beverage to cool down. Okay? Neat. Okay? To get the solid to go to the liquid, what am I doing? I'm adding heat. That's why it's changing phases. Well, if I want to increase the ability for something to dissolve, what should I do to the temperature? Increase it. To dissolve, I'm taking a solid, making it roughly a liquid. If I increase temperature, what's happening? I'm taking a solid and making it turn into a liquid. Those two things are synonymous with each other, which means we can look at the ability for a solid to dissolve in a liquid with respect to temperature. And very commonly, when we increase the temperature, the solid also increases solubility. And so what we're looking at on this curve, or that line, is the mark for maximum solubility. So if I look at, say, that point right there, what I'm saying is that at 80 degrees Celsius, 350, grams of sugar dissolve in 100 milliliters of water. That's what that curve means. That is the most I could possibly dissolve in it. Okay? So I would call that point saturated. Okay? I am saturated with food when I literally can eat no more. Okay? I'm now fully saturated. Have you heard about saturated fats? What are they talking about? When the molecule is literally full of hydrogen. That's a saturated fat. You've put so much hydrogen into the structure, there's literally no other space to put hydrogen. If I look at unsaturated fats, what happens? I've removed some hydrogen from the structure, so there's now places where I could theoretically put hydrogen. So the difference between saturated and unsaturated fats, it literally boils down to 2 hydrogen atoms. That's it. So when we talk about the different health effects of those, all it's coming down to is 2 atoms. Chemistry is kind of a big deal. Okay? We have to evaluate how those subtle changes turn into huge structural changes. All right? So we're looking at saturation there. What if I'd only dissolved, 200 grams of sugar at 80 degrees Celsius? So now I'm looking at that blue dot, right? Could I dissolve more? Yeah. So how might I describe that blue dot? Should I call it saturated anymore? No. There's the potential to shove more sugar into it, right? Which means that blue dot is unsaturated. Okay? Both of those, I think, make sense, but then we also see this extra term floating out there. What's that extra term? Supersaturated. Okay? This means I've put more sugar into the solution than the saturation limit. Okay? So that's saying I am so saturated with food I cannot eat anymore. Oh, but dessert. I'm going to eat some dessert. Okay? And I'm now becoming super saturated. Okay? How does that happen with a solution? Okay? We usually have to trick it into that supersaturation limit. Okay? To trick it, what we can do is heat it up. Okay? We can heat it up to 80 degrees, and I'm going to dissolve 350 grams in there. That's not supersaturated, that's saturated. I agree, but we aren't done yet. Now what we're going to do is slowly cool the solution down. Okay? If we look at temperature, temperature's on the x-axis, so we're talking about cooling it down. We're going right along here. Okay? And let's go to room temperature. We'd be at this point, that little red dot. If I've done this properly, what happens to the sugar? It should have.
It should have gained, or like, it shouldn't have dissolved as many grams, right?
But I've already dissolved it.
So shouldn't it gain it back?
So something about the sugar should have changed. We should have seen roughly 150 grams of sugar come out of solution. It should have precipitated. But if we've done this process carefully enough, what happens? We can trick the sugar molecules into staying in solution. Okay? So that point now is supersaturated. Okay? Well, why would we do this? Okay? Fun little science experiment. What can we do now? Like, dude, I've never done this before. I bet at least one of you has done something like this.
Is this the thing that makes like little crystals?
We could take a little bit of string, tie it to a little stick, submerge the string into the liquid, put that at the top of the jar, and just let it wait. What happens? Little crystals start to grow all over the string, and we end up with rock candy. Okay. Oh, look at this. I've got this magic crystal wand. You can even see them on sticks. I don't know why people would do that. Maybe it's easier to hit people with them. Violent, I guess. Okay. What we're doing is taking advantage of that supersaturated solution. By putting in a secondary thing for the crystals to grab a hold of, what we've done is we've convinced the solution, hey, you know what? You actually screwed up. You shouldn't be dissolved. Here, come here. I will help you crystallize out. Here's a thing that you can grab a hold of so you can crystallize. That's why it crystallizes on the string. It's a nucleation point. It's a place where all of those crystals can come. And that's how we get those rock candy kind of devices that look like pretty crystals, because we've convinced the solution that it should come out. Are there other ways we could convince the solution? Remember our hot ice idiot? Okay. What he did is he created a saturated solution. Okay. Then he cooled it down. We now have a supersaturated solution. How did he convince it that it realized it needed to crystallize out? He put his hand in it. Putting his hand in it provides enough of an agitation within the system that it now goes, oh crap, I'm not supposed to be dissolved. Let me crystallize out. That process in that case happened to be highly exothermic, and the idiot burned his hand. Okay? But we're getting the same kind of process. It's looking at how we shift around that solubility curve. Okay? Most substances, when we look at temperature, will increase solubility when we increase temperature. Why? Well, dissolving something is effectively taking it from a solid to a liquid. Increasing temperature should take things from a solid to a liquid. So it makes sense for them to both kind of agree with each other. Is that true for all substances? No, we got one down here. So there are almost always exceptions, and those substances have weird aspects going on with their structure, which means people tend to study those to figure out why they're going against trends. Okay? Because you could potentially get cool properties out of those systems. Okay? But that's what's happening with our solubility curves. Okay? So as fun and exciting that is, now what we have to do is, what do we do once we have these solutions? We're going to take that stuff that we talked about with all those conversions and equations and all that fun stuff and now bring in solutions. Okay? And therein lies our problem. Okay? If I look at this reaction and I want to measure either the aluminum tribromide or the silver nitrate, what units am I going to use to measure them? So I want units to measure either of those two substances. Or if it helps, you can even throw this one into it. Throw this one in, but no, I'm giving it a different color. I wonder why that's the case. I got 3 different substances underlined, though, so I don't accept that a different substance causes me to use a different measurement.
Well, the last one that you underlined is a solid, whereas the other...
So not a different substance, but a different phase of matter.
Yeah, different phase.
Okay? Does the phase of matter dictate what units I would use to measure it? Yes. Would I use distance to measure any of those?
No.
No. What would I use to measure? What are my units? Measurement units. We could use moles. Moles would be a phenomenal unit because that would allow me to use the chemical equation. So I really like the idea of moles, and that's an awesome suggestion. So I go into the lab and I measure out moles. Nope, can't do it. Because moles is a counting, and in fact a very large counting. Okay, I haven't done the math, but if you tried to count a mole, you would probably die thousands of times over, okay, before you counted to a mole. Okay, so we're not going to be able to individually count atoms. Okay, so mole is a fantastic unit, and we want to hold that thought because that's useful for our conversions. Okay, so we can't use moles. What other measurement units are there? Grams. What phase of matter would I use to measure grams? Solids. Okay, I can scoop things onto a balance that are solids really easily. Okay, so that would make sense, say, for the silver bromide. This one would be useful in grams. Okay, how about the ones in red?
Volume?
Why would I use volume and not grams
Well,
or mass?
if it's aqueous, there's a liquid substance to it, so it's determining how much
It's
space
a
does it
liquid.
fill.
What happens when you try and pour a liquid on the balance? The liquid just runs everywhere and destroys the balance. That's why you don't do it. Okay? So we would use volume. Volume is the category, but not the unit. The unit we would use would be, okay, liters, which I'm also going to balk at. Why would we balk at liters?
Because it's big.
That's a huge amount of volume.
So milliliters.
We would use milliliters. Okay? That would allow us to now measure that. That's fantastic. Okay? What is the volume I'm measuring? If I look at the silver nitrate, am I measuring just silver nitrate with that milliliter measurement?
No.
What else am I measuring? Because you said no.
Are you measuring it with the aluminum nitrate?
No. Say it again. Water. It's an aqueous solution. As an aqueous solution, if I measure the volume, I'm not getting the volume of silver nitrate. I'm getting the volume of silver nitrate with all of the water that's part of it. Is water in the chemical equation as a reagent that's doing something? No. So would I be able to use a milliliter measurement of the silver nitrate to do any kind of conversions? No, that milliliter measurement is incorporating water into it, and water's not part of the chemical equation. So I need some way to get water removed from my equation. Right? So I would need a different conversion factor to tell me how much silver nitrate in that solution there was. Okay? So if we think about that again, how much silver nitrate equals our total volume? Okay? That's the conversion I need. Okay? What unit do I want for the how much silver nitrate? Zeke? Why moles? What do I want to do with silver nitrate? Just stare at it? I want to convert it into what? Not quite. Silver bromide. Why do I know I want to convert silver nitrate into silver bromide? That's what the chemical equation means. Okay? To use the chemical equation, what unit do I need to be in? Zeke? Moles. Okay? So if I'm going to look at this conversion factor, because I know I'm going to need moles to do a conversion, it probably makes sense that my how much of silver nitrate should be moles of silver nitrate. Okay? Now the volume of the solution. What units should my volume of solution be? That one becomes kind of harder to deal with. Okay? It could be milliliters. Okay? So if you were going to work in the industry or say in our stockroom and prepare chemicals for you guys to use, do they only make chemicals in milliliter volumes? No. If we look at the entire Chem 130 curriculum, we're looking at something like 30 labs. That's an overstatement. I think it's closer to 15 labs. 15 different lab sections. Each of those lab sections has 10 groups in them, each of them using 10 milliliters. If we scale that up, that's looking like we're probably going to start to need larger volumes of solution. We'll probably need on the order of liters of solution. So when we look at a larger scale, what we're talking about here is the amount moles of silver nitrate in the liters of a total solution. That conversion factor is going to be dependent on, well, how much silver nitrate you put in and how many liters of solution were there to begin with. So that conversion factor will change every time. And it's going to be dependent on whoever prepared the sample or that solution. Are you going to prepare any solutions in this class, in the lecture? No, which means that conversion factor will very likely, sort of already done, yes, be given to you. Okay? Because this is a very important conversion factor that allows me to relate the moles of a substance to the liters of a solution, I come up with a new name for it. God, another new name. The relationship between mass and volume was such an important relationship that what did we define the relationship between mass and volume to be? Density. We've already done it in the past. We're doing it again. Okay? What is that new term that we invent? Molarity. The symbol we use for molarity is a capital M. Okay? And as soon as you see that capital M, you should immediately write moles of your substance over liters of the solution. Okay? Not moles / liters, moles over liters. Every time. Why? Have you seen capital M before? Have you seen moles before? Okay, one person, 2 people said, yes, we've seen moles before. Have you seen liters before?
Yes.
Yes. Which unit system is more valuable? The one you haven't seen or the one you have?
The one we have.
The one you have. So probably a good first step, write it in something you have seen. That now allows you that format to convert and deal with those systems. Okay? So let's take a swing. What is the molarity of a solution containing 24.0 grams of sodium hydroxide and 0.100 liters of solution? What do I want? Molarity of what?
Solution.
What's in that solution?
24 grams of sodium.
It's the molarity of sodium hydroxide. What did we say we should do with molarity as soon as we see it?
Change it to a capital M.
Nope, I did not say change it to a capital M. I want the moles of sodium hydroxide over liters of solution. Okay? Am I given either of those pieces of information?
Yeah, you're given,
Keep talking.
you're given our 0.10 liters of solution.
Okay, so what do I want? Moles of sodium hydroxide over liters of solution. What do I have?
You have the liters of solution
Where should the liters of solution show up?
in the denominator.
Why?
Because for the equation it's written in the denominator.
For what I want, liters of solution is in the denominator. What shows up in the numerator?
1.
1, because that is the single piece of information. Okay? What do I want? Moles over liters. What do I have? Liters. Do I need to do something? Yeah, what do I need to do?
I need to do another conversion
What do I want? I want moles.
of sodium hydroxide.
Okay, am I given moles of sodium hydroxide?
No.
Okay, so what do I have? I don't have moles of sodium hydroxide. What do I have?
You have 24 grams.
No. What do I have?
You have grams.
I have grams of sodium hydroxide. Okay, and the reason why on the no, you're now saying, oh, I'm going to put a number in. No, we're putting the unit in. Do I have a conversion factor between moles and grams? Yes. What'd you do? Yes.
So, wouldn't it be
Oh, you're killing me.
one mole, or the first one would be in the numerator, because it would go with the moles,
Where are you getting that?
based upon the AMU, isn't it? Or the atomic mass.
I like where you're going with that. What you're saying is that that conversion factor exists where?
In the periodic table.
On the periodic table. Where did the 0.1 liters come from? Because I forgot to put that one in there.
The equation.
That was given information. I have a conversion factor between grams and moles. I'm not using the 24 grams of sodium hydroxide because I'm not using just 24 grams of sodium hydroxide. I'm relating moles to grams. Where do I find that conversion? That's the periodic table. Periodic table says 23 for sodium. I'm rounding. Oxygen is 16. Hydrogen is 1. 40?
Yeah.
40 what?
Grams.
Half right.
Grams NaO or NaO3 or Na sodium hydroxide.
Okay, so now you're half right.
So is everybody tracking this or just James? Just checking. 'Cause he's rattling off things left and right, but nobody else is. So is everybody else tracking?
So over 1 mole.
Okay, so somebody fix it, other than James. Periodic table tells me that relationship. How do I use that in my conversion factor? Wow. How do I use that in my conversion factor? What shows up in front of moles? Not James. I said another way. Let's look in red at the thing that says moles of sodium hydroxide. What shows up in front of that? 1. Where should the 1 go? And be careful with your wording.
I would put it for the denominator. When
No.
it's at the bottom.
No.
Well, on here it'll be at the top, and then the 40
No.
will be.
In front of the unit that it's tied to.
Okay.
Okay? So there's no top and bottom. It's in front of the unit that it's tied to. In this case, I'm talking about moles, so I need to place the 1 with moles of sodium hydroxide. Don't start being, well, now I want to shift things. No, the process was established. What shows up? Where does the 40, or try again. What shows up in front of grams of sodium hydroxide?
40
40. So where does that show up in my conversion?
in front of. Yeah.
No, use your words. You got it.
In front of grams of sodium. Yeah.
No. Where does the 40 show up? You got this all the way out. You're right, but you're letting people finish you. Don't let them finish. I want you to say all of the words. Where does the 40 show up? This 40 needs to show up where up here? You're right. You are right. I just want you to say it all together. The 40 shows up in front of
Grams of.
Now you got added pressure. It's okay.
Forget it.
No, we're not forgetting it. You're coming along for the ride. Grams of,
That's sodium.
that is sodium. That is sodium. So grams of sodium. Did you get it?
No.
Oh, you totally got it.
Blue out here. Yeah. Grams of sodium peroxide.
There we go. Yes, grams of sodium hydroxide. Come on.
That's what you were doing?
Come on.
I was like, what is he doing?
Grams of sodium hydroxide. There it is. Okay? And all too common, what I'll see people do is, oh, I'm going to start changing. No, the units drove that calculation. That tells you where to place the numbers. Don't start now shuffling things around. Okay? When we drew this out, we wrote those units there for a reason. Don't start manipulating and saying, well, I don't like that reason. If you don't like that reason, you need to erase all of your work and you start again from the beginning. And that's okay. But we had solid reasoning through that. Would we now have our answer? Do I have moles of sodium hydroxide in the numerator? What do I want? Yes, awesome. Do I have liters of solution in the denominator? What do I have? Yes. Grams of sodium hydroxide shows up. So what do I have? What do I want? What do I want? I don't want grams of sodium hydroxide. So what do I have? Grams of sodium hydroxide. Do I just have grams of sodium hydroxide? Yes. It is 24 grams of sodium hydroxide. Says it right in the question. Now the 24.0 grams of sodium hydroxide comes in. What can I do? I can get angry and punch the calculator and do numbers until it spits out a number that I agree with, and I circle my answer. Okay? That work should be there. Okay? If you are struggling to get answers, it's because you're not showing work and you're not following those steps. What do I want? What do I have? What do I want? What do I have? All the way through. Okay? Somebody actually want a number on this? Yeah, you want a number? Damn it. I don't have a calculator. Everybody has phones, not calculators. $24 divided by 40 divided by 0.1. We get 6 moles per 1 liter of solution. What is moles per liter equal? Molarity. And what is our symbol for molarity? Capital M. 6 capital M sodium hydroxide. Which, before you tell me I'm wrong, I know. Shut up. 6.00 molarity of sodium hydroxide. Zeke was like, oh yeah, you made the same mistake I did. We had to watch out for our sig figs. We had 3 sig figs. Okay? So that means we could totally do another one really quickly and easily. How many grams of potassium dichromate are in 125 milliliters of 0.15 molar potassium dichromate? What do I want? Anybody else like potassium dichromate? That's a lot of stuff to write out. I don't want to write all that out. KCR works for me. Right? It's an abbreviated notation. It's not valid, but this is work. I can use whatever symbols or notations I want as long as I make sure to make that final translation. Okay? So, grams of potassium chromate. We've got a bunch of given information. What given information do you want to start with?
Thinking maybe 0.150.
0.150. molar. And that's already nasty, right? That stupid capital M, so we shouldn't have boxed that. That was dumb. Mike was an idiot. Is an idiot. Use whatever verb you like. Moles potassium chromate over 1 liter of the solution. Yeah? So why are you picking moles of the potassium chromate as opposed to the milliliters of solution?
I just want to get it over with,
I don't follow that logic.
For the milliliters, you still have to do a conversion to convert it to liters. So at least with the .150 molarity, you can leave it at that, right?
What is the substance in blue?
The molarity.
What is the substance? Molarity would be a measurement. What is the substance? Potassium chromate. What is the substance for the milliliters? This is a hard one.
You don't know.
It's not clearly specified, but it is there. It's that milliliters of solution. It's the potassium chromate and water. That's a solution. What is the substance I'm solving for?
Grams.
The potassium chromate. Okay? Grams is the measurement. Substance, potassium chromate. Does the 125 give me the substance?
No.
Nope. So I'm going to argue I don't want to start with that. But it doesn't give me the substance. Okay? Perfectly legitimate answer. Okay? So I would argue that we could start with the blue. Okay? In the blue, where do I want my substance to show up? Why do I want it on the top?
because it's
If we look at our answer, where does our substance show up? In the numerator, which means put it in the numerator. KCR, this would be moles. What's the unit I'm tying it to? Liters of solution. This was 0.150 moles per 1 liter. Where was that information found?
That was given.
That was given information. What do I want? Grams of potassium chromate. What do I have? Moles and liters. Okay? We got two choices. What do you want to focus on? Okay? So now Kira's taking over James. What do we want to have? What do we want? Grams. Thank you, Krista. Potassium chromate. What do I have? What do I have? Moles of the potassium chromate. Where do I find the conversion factor between the grams and moles? Yes, periodic table. In a show your work, you're like, damn, I don't know how to do that. There's too many things, I'm confused. Write that. You've now told me that you know where to get this information and you're missing a key step. That's cool. Okay? You've at least acknowledged that you know what you're attempting to do. Okay? So I'm going to say, I don't even care about the numbers. So we're not even going to bring those in yet. Okay? What do I want? Grams of potassium chromate. What do I have? Grams of potassium chromate. And liters of solution. Do I want liters of solution? No. So what do I got to do?
Another conversion.
I got to do another conversion. Liters of solution. Why am I placing it in the numerator? So that it can cancel with the liters of solution in the denominator. What do I have? Milliliters, which means milliliters of solution. What is the relationship between milliliters of solution and liters of solution?
One over 10
Pick a system that allows you to memorize that. Okay? That information is found ultimately from memory. Do what you got to do to memorize that. Okay? And ultimately, I don't care what you do with that memory as long as you've memorized it correctly. But that has to come from memory. Okay? What do I want? Grams of potassium chromate. What do I have? I have grams and milliliters. Do I want milliliters? No, so what has to happen?
Need another conversion.
I need milliliters of solution here so that it cancels. What do I have?
Nothing.
Look in that red box in the question. 125.0 milliliters of solution. This was given. Now what happens? If I've put all of the numbers in through my conversion, now I can multiply it out. If I haven't put those numbers in, what do I need to do? Find them. Pull that information from my memory. If we use my memory for this, I told you 10 to the negative third for means milli, which goes with our core unit, liters. The grams per mole. Can anybody do that math that fast? I'm going to say that's a no. 8200. 16 times 4 is what, 64? Another 2, so we're 90-ish, so we're about 280. 280 grams of potassium dichromate is 1 mole of potassium dichromate. For those of you that aren't checking that, you need to check that. I just did that math in my head, right, and made lots of rounding. What is that?
It's 294.
294? 280?
It's close.
Stop encouraging him, Kira. Now we can punch it into the calculator and run through our numbers. Okay? That's the process we have to work through. Okay? So, we're not going to look at this one right now. We're going to save this one for later. This is kind of a larger assignment. This is ultimately what you will do in lab in 2 weeks. Not 2 weeks, next week. Okay? You're going to be doing this question, okay, in lab. Okay? The little he thing meme is because we were going to make this a larger assignment. Okay? Trying to evaluate your process for how you would go through and solve this. Okay? We're out of time to be able to start pushing this process at you. We have to start catching up, unfortunately, which means we're not going to look at that whole breakdown or make you go through and do that whole breakdown. Okay? If we have time in the next 2 lectures, we'll go through and look at that question on how to go through and solve it. We are not done today because we're going to look at gases. Okay? When we move to gases, we've got our properties of gases. All of those are familiar. The only new thing on that slide is right there at the bottom. Gases can and do exert a force on the container that holds them. That force we call pressure. Right? So we now have a new measurement because we can look at pressure to represent our gases. Okay? Before we start pushing into what that pressure means, what we want to do is take a step back and say, well, gases can do some crazy weird stuff. Let's just go through and make it as ideal as possible. Just like humans can do some crazy weird stuff, can show up drunk, punch people and all that. Okay? Stab, kill, maim, murder, all that fun stuff. We don't make the assumption that everybody's going to do that. And you all are perfectly aware that you're making that assumption because, well, at least you two are making that assumption. The rest of you might be not making. The rest of you might be making that assumption. Why are they not making the assumption that everybody's going to punch, kill, murder, and maim?
Sitting next to each other.
They're sitting next to you. The rest of you are like, damn, I'm not sitting next to him. He's going to kill me. Okay? You're at least making the attempt to say you're in a classroom full of people. If you were making that assumption, that would be dangerous. Okay? So we look at an ideal situation. That ideal situation makes life a little bit easier. First one, gases, super tiny, they have no volume. Okay? Kind of a weird one to make, but that's true, or that's our assumption. They move in random directions and in straight lines, which kind of ties in with the next one. Gases have no attraction for each other whatsoever. Okay, so if we imagined ourselves as gas molecules when we walked in here, okay, where would you sit every day?
In random spots.
In random spots. Everybody would be moving to different spots throughout the classroom. Is that true?
No.
No. You've all been sitting and gravitating to certain locations throughout the semester. So you do have some attraction with your environment. We're making the statement that gases do not have that. Okay? Gases collide without losing energy, and the average energy of our gas is proportional to temperature. You increase the temperature, we increase the energy. Okay? If we make all of those assumptions, this nasty little equation comes into play. That nasty little equation showed up in chapter 8 and in 9, and I told you to ignore it in the hopes that we would actually get to it before you had to use it. Okay? Unfortunately, you've probably had to go back and use it in our homework questions. Okay? You will be responsible for memorizing that conversion factor. I will soapbox the hell out of that thing in our next class period. We're going to move through the rest of chapter 10 on Thursday, and I'm going to pick up the pace a lot to try and cover content so we can spend next Tuesday reviewing and practicing more than talking about content. So with that, we got to stop.